Hello and welcome to GCSE Chemical Reactions with Mrs. Castanera. We're on lesson 2, Reaction of Metals with Oxygen. Our keywords for this lesson are oxidation, reactivity, ion and metal oxide. So I'd like to start the lesson by answering the 8 questions in the knowledge check and pausing the video whilst you do that. Okay, so let's go through those. Question 1. State what happens to metals in redox reactions. So they lose electrons. Alternately, you can write oxidation. So either of these is correct. Lose electrons is more of a higher tier answer, and oxidation is more of a foundation tier answer, but it really doesn't make a difference as long as you've written one. Question 2. Define a redox reaction. So that's when reduction and oxidation occur at the same time. And I've written in capitals RED from reduction and OX from oxidation. To remind you, that's how the word redox is formed, from RED and OX. So it's when they occur at the same time. Question 3. Complete. When atoms lose or gain electrons, they are called ions. Question 4. Explain why there is no reaction between MgO, magnesium oxide, and Au, gold. And that is because Mg, that's magnesium, is more reactive than Au, gold, so the gold can't take the oxygen away from the magnesium. Question 5. State what happens to nonmetals in redox reactions. Well, they gain electrons, or you can write reduction occurs. Question 6. State the symbol for an electron in a half equation. So it's that lowercase e with a negative symbol at the top. So that's what an electron looks like in a half equation. If you're foundation tier, I wouldn't expect you to have written that, but if you did get that, well done. Question 7. Define a displacement reaction. So a displacement reaction is when a more reactive element replaces a less reactive element in a compound, such as oxygen moving from a less reactive metal such as copper to a more reactive metal such as iron. Question 8. Name the bonding between metals and non-metals. Well, that is ionic bonding. So give yourself a mark out of 8, please, and then we're going to move on. So today we are going to be able to describe and explain the reactions of group 1 metals with oxygen. Now, group 1 metals are the first column in the periodic table on the left-hand side, and it contains materials such as lithium, sodium, potassium, rubidium, cesium, and francium. So we're going to have a look at the reactivity series of metals now. So we have looked at this before. So the reactivity series is all about metals reacting with other substances. So when metals react with other substances, the metal atoms form positive ions, and that is because they lose electrons. We're going to write a note about this. So they lose electrons to give themselves a full outer shell, or in fact, in this case, really more of an empty outer shell. And those electrons are donated to the material they're reacting with, to the other element. So, for example, you might react sodium, a group 1 metal with 1 electron in its outer shell, with chlorine, a group 7 element which has 7 electrons in its outer shell and is missing 1. So a single spare electron from sodium joins the outer shell of chlorine, and then both elements have full and complete outer shells. The metal has formed a positive ion because it has lost electrons, and the non-metal, chlorine in this instance, has formed a negative ion because it has gained electrons. And we'll talk more about this later on in the series of this topic. But essentially, metals form positive ions. Now, group 1 metals form positive ions with +1 charge because they only have 1 electron to lose. Group 2 metals, that's the second column in the periodic table, they have 2 electrons in their outer shell, and they will form positive ions with +2 charge because they have lost both those electrons when they form their positive ion, when they react. So the reactivity of a metal is related to its tendency to form positive ions. Now, this is a really important statement, but it doesn't necessarily make a lot of sense without the understanding behind it. So, the reactivity of a metal is related to its tendency to form positive ions. Now, group 1 elements, for instance, the reactivity increases as we go down that group because the atoms become larger and the outer electrons are further from the nucleus. And that means the force of attraction between the negative electron in the outer shell and the positively charged nucleus gets weaker the further away it is from the nucleus. So the bigger the atom, the weaker those outer electrons are bonded into that atom. So the outer electrons are lost more easily in bigger elements. We're going to write a note about that. Okay, so as you can see, I've written that. The outer electron is lost more easily from bigger elements. And then I've added more information, so elements get bigger as you go down the periodic table. What I want you to do is I want you to make sure you've written that down. Pause the video if necessary, so you've got that written down, please. This is really important information. Okay, moving on. So metals can be arranged in order of their reactivity in a reactivity series, and this here is the reactivity series from most reactive to least reactive. So at the top of our reactivity series we have potassium. Potassium is the most reactive element in this series, and you can find potassium lower down in the periodic table. There are more reactive metals that aren't in this reactivity series, such as rubidium and cesium and francium, but these are very rare and we don't deal with them day to day because they are very dangerous chemicals to be using. So we're talking here about the ones that you will see in GCSE science and learn about and use. So potassium is more reactive than sodium, which is more reactive than calcium, and this continues until we get to a non-metal, which is carbon. Now, all of these 5 metals, from potassium to aluminium, are more reactive than carbon. Then, below carbon, we have zinc, iron, tin, and lead, which are all less reactive than carbon, but more reactive than hydrogen. And then, less reactive than hydrogen, we have copper, silver, gold, and platinum. So there's a few things to know about this, and there's a reason we've put carbon and hydrogen into this reactivity series. So the metals here below hydrogen that don't react with hydrogen, they are found native, which means that we can find them as just lumps of metal in the ground, not reacted with anything. That's what native means, unreactive metals, so just a lump of gold or a lump of silver. And that is because they do not react with hydrogen. So they don't react with water, they don't react with hydrogen, they don't really do anything. And so because they don't react when they're in the ground or in a river, we just find them as lumps of metal. So we're going to make a note about that. So I've written in that metals below hydrogen are found native, which means unreacted, such as a lump of gold. And these were the first metals to be discovered by humans and used by humans because we literally just found them shining in the ground. A rainstorm would help wash away the dirt and show shiny metal in the ground, and those were the first metals to be discovered and to be used. So that's why even back in very old times, such as the Bronze Age, we had people using copper, silver, gold as currency or as jewellery and objects. So next we're going to look at these metals between hydrogen and carbon, so zinc, iron, tin and lead. Now these ones do react with hydrogen, so you don't just find them as lumps in the ground. Often, because they react with hydrogen, they'll also react with oxygen, although so do these ones. Now these 4 here, they all are found as an ore. Okay, so an ore is when a metal has reacted with materials from the earth and you have to extract it or remove it from its ore to use it. And the way we extract these from their ore to use them is by heating them with carbon. So we can use carbon to extract them from their ore, to remove them from their ore so that we can use them. So it's a bit more complicated than these ones, which you just have to dig out the ground. But again, we did manage to use this quite a long time ago, even in the Iron Age, which is a long time ago. So we're going to write a note about that. So you can see I've written here that metals between carbon and hydrogen, which is these four, can be removed from their ore by heating with carbon. So if you make sure you've written both of these down, please, if you haven't already. And then we'll move on to the elements that are metals in particular that are more reactive than carbon and how we can extract those from their ores. So as you can see, I've written that metals that are more reactive than carbon, which is these ones here, can be removed from their ore by electrolysis. That's using electricity to remove them from their ores, because it requires a lot of energy to remove these from their ore because they're so reactive. So to get them back to just being individual metals, so giving them back their electrons, requires so much energy, we have to use electricity. And so these metals were discovered much more recently once we had electricity. So make sure you've got all that written out and copied out, and then we'll move on. Pause the video if you need to do that. So moving on to page 15 now. The metals potassium, sodium, lithium, calcium, magnesium, zinc, iron and copper can be put in order of their reactivity from their reactions with water and dilute acid. So these metals here, we put them in order of their reactivity by looking at their reaction with water and their reactions with dilute acids. The non-metals, hydrogen and carbon, are often included in the reactivities, and you've seen why. I've explained that, and that's about how we extract them from their ore, and it's really important to know that. And the reason we've included them, and the reason that this works, is because more reactive metals can be displaced by more reactive metals can displace a less reactive metal from a compound. In this case, when extracting those metals with carbon, because carbon is more reactive than the metal, the displacement reaction means that carbon is taking away whatever those metals have been bonded to and is leaving us with pure metal behind. Okay, so there's some videos to watch now. So we're going to learn a bit more about the Reactivity Series and also about chemical reactions. So there's two videos here. If you have a digital copy of this booklet, which is accessible to you through your online learning group, through Teams, or ask your teacher, if you would like a copy of the book digitally. Or you can just type in Fuse School or go to the Fuse School section of YouTube and look at Reactivity Series of Metals. And there is also the Fuse School Displacement Reactions and Reactions in Solutions. You should be able to type those into YouTube and the correct videos should come up. So pause the video whilst you watch those, please. So hopefully after watching the videos you have a much better understanding about reactivity series, displacement reactions and the reactions of various metals. So we're looking now at the reactivity of magnesium with oxygen. So we've seen magnesium reacting with oxygen and forming magnesium oxide. Okay, so magnesium reacts with oxygen to form magnesium oxide. And here is the equation for that. So magnesium plus oxygen turns into magnesium oxide. Because oxygen is a diatomic molecule, O2, we can't write just O, it has to be O2. So because of that, we have to have two magnesiums and two magnesium oxides as well, because there's only one oxygen attached to the magnesium. So the magnesium atoms lose their two valence electrons. Now remember that valence electrons are the outer electrons, and that's from their highest energy level, not from, but from their highest energy level to oxygen, which gains those two electrons. So those electrons are donated from the magnesium to the oxygen. Now both the magnesium and oxygen become positive and negatively ion positive and negative ions respectively. So the positive ion is magnesium because it's lost its negatively charged electrons. The negative ion is oxygen because it's gained 2 extra electrons. And I've written that in, so we've got Mg, and I've put a little thing at the top there, it says 2 plus, and here is O, and this time, because it's an ion, we actually do talk about it in single form, bizarrely. So it's just O, and at the top it's a 2 minus, and this shows that magnesium is positively charged by 2 because it's lost 2 electrons, and the oxygen is negatively charged because it's gained 2 electrons. And so because these are now oppositely charged, they are attracted to each other via electrostatic forces. Okay, electrostatic forces are the forces between positive and negative or oppositely charged things. So they will attract to each other and form magnesium oxide. So make sure you've got all those notes down and you've done all the highlighting. So unfortunately, we can't see the next observation of magnesium and oxygen reacting. However, if you want to see this, you can literally type into YouTube magnesium and oxygen, and you will probably be able to find very quickly an example of magnesium burning in oxygen. You should already observe this from the Reactivity Series of Metals video, but if you want to see it again, or specifically just that, you can type it into YouTube, and then if you do get to see that, you could fill in some of your observations. But because not everyone can do that, we're not going to do that during this lesson. If you do have any questions about that, please feel free to email your teacher or ask us on Teams, and we're very happy to help you with that. Okay, so we're going to move on to reacting group 1 metals with oxygen. So, you can also show how reactive other metals are by heating them in oxygen and observing the kind of reaction. So group 1 metals will easily lose their 1 outer electron. But the larger atoms further down the table will lose theirs more easily. We already discussed this. Larger atoms lose their electrons more easily, and so they're more reactive. And this is because the attraction between the positive nucleus and the negative electron becomes weaker as the distance between them increases. Okay, so that's really important to remember that and to understand that. So further down the periodic table, where the elements are bigger, and the outer electron is much further from the outside of the from the center of the atom. It's much further from the nucleus, that outer electron, and that nucleus is positive. The outer electron is negative, so they're attracted to each other. But when that element is very big and that outer electron is really far away from the nucleus, that attraction becomes quite weak, and so that outer electron is lost very easily compared to a much smaller atom. So now we're moving on to page 16. Again, this is a reaction between group 1 metals and oxygen. You have seen some of these. Again, if you want to watch these, you can type this into YouTube, group 1 metals and oxygen, and you should be able to see some examples of this. You could have a go at these questions. We're not going to go through these at the moment because this is very much practical activity, but if you want to, you can use YouTube to help you do this. And it's nice to see these examples. And I imagine when we're back in the classroom, we will go through some of these, and so you can see them at some point in the future. And that continues on to page 17. And so the next activity we're going to do is learning activity 1, which is all about writing equations for the reactions of metals and oxygen. So, when metals react with oxygen, they form metal oxides. We know this from last lesson. So metal plus oxygen turns into metal oxide. And we're going to write that out. So I'd like you to write that out too. So this is the equation. You can substitute any metal for the word metal. So aluminium plus oxygen turns into aluminium oxide. Iron plus oxygen turns into iron oxide. Okay, so this is a really standard way of saying it. So you should be able to use this to help you complete the word and symbol equations for the reactions of metals and oxygens. And, this is very important, you will need to check if they are balanced too. So have a go at those, pause the video whilst you complete that activity, make sure you check you have the same number of atoms before and after the reaction. So if there's 2 oxygens here, there must be 2 oxygens here. If there's 2 magnesiums here, there must be 2 magnesiums there. And so this is 2 sets of equations, word equation followed by the symbol equation, and then another word equation followed by another symbol equation. So pause the video whilst you do that. So let's go through that. So we have 2 magnesium, which must be a capital M and a lowercase g, and you must have 2 of them. And magnesium oxide was what you needed to write here. Okay, and then next we have calcium plus oxygen to form the calcium oxide that we're given, and 2 lots of calcium, O2, and 2 lots of calcium oxide, which is CaO. And C must be capitalised, and the A must be small, and the O must be capitalised. So there are 6 marks here. No, there's not 7. 1, 2, 3, 4, 5, 6, 7. So give yourself a mark out of 7, please. Okay, so checkpoint question. Pure lead sulfide is heated with oxygen. This chemical reaction makes lead oxide and sulfur dioxide. Write a balanced symbol equation for this reaction, including state symbols. That's worth 3 marks. So it's got to be a symbol equation, it's got to be balanced, and you need the state symbols. So to remind you that state symbols are S for solid, L for liquid, G for gas, and sometimes you use AQ for something that's dissolved in water. AQ means aqueous, which is just Latin for water. And part B, explain whether lead oxide is oxidized or reduced. So you have to state whether it's oxidized or reduced for 1 mark. For the second mark, you need to explain why. Also, lead sulfide is PBS, just so that you know what it looks like. Okay, so pause the video whilst you do that. Okay, so let's go through those. Question A, this was a really tough question, okay? Even for higher tier students, this was tough. Okay, so don't stress if you just totally screw this up, okay? Because it's a good activity to learn from. So first of all, I gave you the symbol for lead sulfide. Okay, now PBS is lead sulfide and O2 is oxygen. Now lead sulfide is a solid and oxygen is a gas, and it turns into PbO, lead oxide, and that is also a solid, and SO2, sulfur dioxide, which is a gas. Most things that are dioxide are gas, like carbon dioxide. Now, to balance this, it was a tricky one. The best place to start is with the oxygens, okay, because there's oxygen is O2, okay. Now, you've got SO2 here, but you've got PbO, so you've got 3 oxygens on this side and only 2 oxygens on this side. Now, you could have 2 lots of PbO, okay, so then you would have 4 oxygens, so 2 oxygens here as part of PbO, and you could have 2 oxygens here, so that's 4 in total, at which point you could just have 2 O2. But then you've only got 1 lead, and so you need 2 leads, so it turns out that when you double up to make 2 lots of lead sulfide, you need 2 lots of lead oxide, 2 lots of sulfur dioxide, and in the end it's 3 lots of oxygen. So you can have 1 mark for the equation with the symbols. So if you've written PBS, O2, PbO, and SO2 correctly, you can have a mark. You can have a second mark for it being balanced, so having written the numbers in red correctly, so 2, 3, 2, and 2. And the third mark the third mark is for writing S for solid, G for gas, S for solid, and G for gas for the correct compounds. So 3 marks there. Part B. Okay, so lead oxide is reduced. So if you've written reduced, you can have a mark. And there's 2 different ways you can write as for the reason why. Because oxygen is lost, that's a good foundation tier answer. It's also acceptable as a higher tier answer. Higher tier students may have written that electrons are gained. That's another good answer, but you can only have a mark for one of these. So this is out of 2. So 1 mark for reduced and 1 mark for the reason. So the total for this section is out of 5. Foundation tier students, I would hope you would have got at least 2, maybe 3 out of 5, if you've done really well if you got 3 out of 5. Higher tier students, I would expect you to get at least 3 out of 5, and you've done really well if you got 4 or more out of 5. As I said, these are tough, tricky questions. So we're going to move on now to the knowledge check, which is also on page 18. There are 8 questions. I want you to pause the video whilst you answer those. Okay, so let's go through those. Question 1, name the compound formed from magnesium and oxygen. Well, that's magnesium oxide, or MgO. Make sure you've got correct capitals and small letters there. Explain why the answer to question 1 is oxidized. Well, that's because oxygen is gained by magnesium, or alternatively, you may have said electrons are lost by magnesium. Question 3, complete the sentence. The list of metals in order of reactivity is called the Reactivity Series. Question 4, name the 2 non-metals in the list from question 3. That's carbon and hydrogen. You need both the answers to get the mark. Question 5, state the most reactive group 1 metal you observed. Well, the most reactive group 1 metal is potassium that we observed and that we're learning about here. Complete the sentence. Metals form something ions. Well, metals form positive ions. Question 7, list the group 1 metals in order from smallest to largest. So it's lithium, sodium, potassium. You only need those 3, or Li, Na and K. That's them in symbol form. So as long as you've got those 3 in order, both either in words or in symbols, you get the mark. And question 8, complete. Metal plus oxygen turns into metal oxide. So that is out of 8. If you could give yourself a mark out of 8, please. So I would hope that you've got probably 5 or 6 out of 8 would be a good score on this. This was not that difficult. Okay, you should know most of these. So higher tier students, I'd expect you to get close to 7 or 8 out of 8. Okay, so we're moving on to the application of knowledge questions on page 19. Question 1, the oxidation reaction of iron and oxygen to make iron 2 oxide is a slow process and forms an orange flaky material called rust. Explain why we paint objects made from iron. So firstly, I'd like to point out that iron 2 is just the same as iron, Fe, and sometimes we use this 2 to indicate that it makes an ion. And iron 2 oxide is just FeO. Okay, so just use that information. It's not really, you don't need to use that information, but you need to explain why we paint objects made from iron. Question 2. Methane, CH4, is the name of the gas used in science labs. That's what we turn on when we turn on the gas for your Bunsen burners. The oxidation of methane produces carbon dioxide and water. Write the word and symbol equation for this reaction below. So you need word equation and symbol equation. Okay, there's a hint here. You may need to balance the symbol equation. Okay, if it says you may need to and it's a hint, it usually means you do have to. So pay attention to that. So pause the video whilst you answer those 2 questions, please. Okay, so let's go through those. Question 1. Explain why we paint objects made from iron. Well, we paint iron objects such as railings around buildings to prevent the oxygen from reacting with the iron and forming rust. So it's this statement here, preventing oxygen reacting with the iron to form rust. Okay, so that's what will get you the mark. So the idea that you need to stop the oxygen getting to the iron, and the idea that if it does, it's going to make rust, and rust is damaging, okay, because it causes the iron to flake away as iron oxide, and that's not good because it means eventually you will have no railings. Question 2. So write the word and symbol equation for the reaction and balance it. So it's methane plus oxygen turns into carbon dioxide and water. So you have a mark for the word equation. A mark for the chemical symbol equation, which is CH4 plus O2 turns into CO2 and H2O, so a mark for that. And then the third mark is for balancing it, so it's 2 lots of O2 and 2 lots of H2O, so you can have a third mark for balancing it. So there are 5 marks here in total, 3 on the second question, 2 on the first, so give yourself a mark out of 5. If you are a foundation tier student, I would hope that you had got 3 out of 5. If you're a higher tier student, then really you should have got 5 out of 5 on this. Okay, so our extension activity then. So your extension activity is to research into the reactions of rubidium and cesium with oxygen. So again, YouTube has some great videos on this. So what I want you to write in the box here is a small amount of information about how reactive rubidium and cesium are with oxygen and what you would observe when they react. So do you see a little fizzling and bubbling, or do you see something else? So lastly, before we go, we've got our keywords for the lesson, so reactivity and metal oxide. Make sure you learn those. You can cover them and try and remember and write the definitions. That's a good way of doing that. So if you have any questions or anything, please email your teacher. We're very happy to help explain anything you need help with, and help you out with any answers you want checking or correcting. So that's the end of our lesson. Thank you very much.